Hey, what's up, Spiceheads? Thanks for hanging out with us for today's webinar, Keeping the Internet Safe and Resilient for You and Your Customers, brought to you by Cloudflare. Before we get started, I do want to remind everyone this webinar is being recorded. Look out for an email from us within a couple days with a link to check out the recording on demand. Also, there's a Q&A box on your screen. When you submit a question, it will disappear from your box and queue up on our side. Don't fret, we do have it, and we'll ask as many of those questions as we can get to at the end of the presentation. However, if we're not able to get to your question live, somebody will be able to follow up with you. Now let's get started. Our presenters today are Martin Levy and Nick Wondra, and our conversation will be led by Tim Fong. So guys, whenever you're ready, take it away.
Great, thanks so much. So I'm Tim from Cloudflare, and many of the conversations I've had with customers, big and small, they often point out that they want the internet to be faster. They have applications, they have APIs, they have mobile websites, and they're interested in Cloudflare because they understand we can help make it faster. But what's interesting is many don't really drill much deeper. They don't understand beyond sort of a very sort of surface level, what are the sources of the slowness? And so after talking with customers, I thought after they've understood better why the internet is perhaps, while a beautiful and magical thing, can also create problems when it comes to delivering applications, and it may only get worse over time as they change their applications unless you address some inherent structural issues within that. So the purpose of this is actually to give you guys sort of a deep dive into understanding, hey, why is sometimes my internet slow? Why is it sometimes when I have my website, I have some customers who have issues and others who don't? And then the second part of this will be addressing, hey, what are some ways that we can solve them? Some of them are pie in the sky by looking at how do you just fix the internet, to how do you actually address them in actionable and tangible ways. So to kick us off will be Martin Levy. He is our part of network strategy, and he's going to give us an understanding of why is the internet slow? What was the sort of core sort of structural issues around the internet? And let us really sort of understand what those challenges are. And then once we frame, hey, these are the problems, here's the complexity. I mean, the internet seems to work great, but there's actually a lot of hidden complexity, which I found when talking to people they don't really understand. And once they do, suddenly the lights go off in terms of how they can solve them. And then we'll have Nick from our team, and he'll talk about ways that you can approach the solution. So I'm going to kick it off here with Martin and just sort of give him a sort of big open question. Hey, is the internet reliable or is it sometimes spotty? And if so, why?
Tim, thanks for the question. I seem to hear that nearly on a daily basis from somebody or other. So today I'm going to I think I'm going to give a little bit of a pessimistic point of view by the very nature of the title of the talk, Internet, Unreliable Internet. And that doesn't mean that it's 100% unreliable, far from it. It is, in fact, actually that when we have issues, that's when we worry about things. And while things work on a day-to-day basis, we want them to work all the time. And it's rather important to understand how certain things actually fail. So my part of the talk today is going to cover sort of how the internet is tied together, even to a certain extent the definition of the word internet and where it comes from. And I'm going to pick down on the topology, the part of the internet that I focus on, which is how all of this bolts together in some form or another and how it operates. I'm going to give some examples of some tools and some pointers, and if nothing else, that's going to give homework for the viewers today, because something very, very important of what you said, Tim, needs to be reiterated. Sometimes the internet works for me, but not for you. Sometimes it works for you, not for me. There is no generalized, does it work for everybody? We sometimes want to drill down and understand what a particular person sees. So I'm going to give some examples of that. So moving along, let's talk about how it's tied together. Let's explain this and make sure that then we can sort of see where the problem space is. And one of the key points is the internet got complicated. Way back when even before we used the word internet and we just used the word ARPANET, you probably could put into one room all of the techies, all of the operators that had everything to do with bits flying around the world to what would have been no more than, to begin with, 100 or so computers, mainly in research areas. Life was easy. That has changed. We now live with approximately 60,000 and growing highly independent networks, all of which interconnect in some way or other. And that collection of networks is where I focus on to make sure that we get reliability. And we do that through various different mechanisms, one of which is diversity, the ability to know that if you need to move bits from one place to another, that you have the ability to use more than one path. And then, even more importantly, that you have a mechanism, a software mechanism, that actually knows how to pick a path. That can be built out of multiple different building blocks, both digging up two different streets and placing fiber, the building block of the internet, into two different places so that hopefully if a problem occurs on one street, it doesn't occur on another. And this is actually quite a common technique. The other ideas are to use diverse hardware. At Cloudflare, we use 3 different hardware vendors to operate our core network. Why 3? Because what if one of them has a problem that replicates everywhere? We want to make sure that doesn't affect us everywhere, so we have to deal with this. And those type of problems have occurred. The internet ultimately runs on hardware running software, and software can have issues. So although the internet has all of this diversity, I'm going to drill down a little bit on it and see how it's used. It also has sort of this vertical diversity. In other words, we have choices of protocols. We're sort of familiar with talking about TCP. We're familiar with talking about HTTP because we type that into browsers every now and again. But there are other protocols that provide other ways of connectivity and getting data from one point to another. So we're going to deal with that as well. But first off, I'm going to deal with just how complicated the topology is. And so I have this simple picture. Now, I call it simple because I've seen worse. This diagram on your screen has a series of boxes, different colors, and a series of lines. And each one of those boxes represents a different part of the internet operated by a different corporate entity, maybe a telco in one country, or a telco in another country, or a mobile operator, or a hosting company. If I was to draw this diagram in completeness for all of the 60,000 plus networks out there, the diagram would be basically impossible to read, and in fact doesn't make any sense. Because to go back to what I said before, you want to diagram the network from where you sit or where your customer sits. There's a lot of places that you don't care as much. So as we look at some of the tools later on, I'll explain how to grab these diagrams. This particular diagram is a working diagram out of a telecom company, a very large telecom company, and you can substantiate pretty much most of that diagram. And their network engineers understand and can manage that and gives their network the connectivity appropriate for their customers and the like. But you can imagine that there are 2 things going on here: their own configuration and their dependency on other players. And that dependency will come up again as we sort of hit some of the other areas. Now, how does a diagram like that even work? How you don't have humans looking at each and every line on that and deciding what to do on a minute-by-minute basis. And the answer is that back in the 90s, through obviously multiple versions, the IETF, the Internet Engineering Task Force, which is the entity responsible for developing most of the protocols that you use on the internet, the protocols at least for moving bits around. The IETF specified a version 4 of BGP, the Border Gateway Protocol. And the Border Gateway Protocol is really the lifeblood of how the internet works. And it's also the lifeblood of how we debug things at the connectivity level. I'm going to point to some tools that will give you some insight into this. But BGP has this ability to handle these enormous routing tables that exist around the world that make up the global internet. Each of those routing tables is unique. The routing table used for Cloudflare is different than the routing table used by a major studio with video, or an airline, or a hosting company in some other random place, or a mobile network in again, some other place. Everybody has their own routing tables, and those tables are linked together through the protocol BGP. They enable the ability for us to grow the internet. That's one of the big works in the IPv6 world, which I'll skip for today, but has been one of my topics of interest for many years. But more importantly, the BGP tables, they're global. They contain every destination on the internet. So if a new mobile provider shows up in a country far, far away and plumbs itself into the internet, it shows up in the BGP tables. And another side aspect of BGP tables, which make it very useful for understanding how things work and then when things don't work, is that the data is very public. The data is has to be public, because in order for me to sit here in our offices and talk on a online system and do a webinar, I have to have an IP address that has been announced to the rest of the world. And that process is repeated everywhere. That data is in fact recorded. That data is saved away by various entities and saved away for research as well as just for debugging, day-to-day debugging. So why does the internet fail at this level? And this is very different, and before I go, with something like somebody's laptop crashes or the software needs updating. We're still focused very much on the plumbing of the internet and making sure that we can get from one place to another place. We have a protocol that enables us to understand where things exist, where paths exist to move bits. BGP, by the way, also has in it the ability to represent commercial agreements, the ability to say, I'm willing to send this traffic this way and different traffic another way, or a relationship between two players has a positive or a financial environment or a $0 environment between two players. You hear two different terms on the internet, internet transit and internet peering. It would be good just to mention those very quickly. Internet transit is the ability, again using the BGP protocol, to say to somebody, I wish to connect to the rest of the world, to everything, and I wish our network to connect to the rest of the world. Peering is the much more subtle case of equal networks that want to interconnect and generate short circuits. That is, in fact, why the complexity occurs. That's actually why those diagrams were more complicated before. But the reality is that BGP handles the growth, whether something happens next to your network or far, far away. I'm going to give you two examples of first the good things that happen. On the screen is a wonderful picture. This was taken in the Seychelles off of the coast of Africa. And here was an undersea cable, a fiber optic cable, which is, by the way, covered in both waterproof material and then metal to protect it. And it operated from the Seychelles back to Dar es Salaam in Tanzania. This is the picture of the cable landing. All the executives got in the water to help pull the cable in from a cable ship, which you can't see. It's a mile or so off land. This is an example of new internet. And this, in fact, would then go into the BGP routing tables. And in this case, the Seychelles suddenly became both much more reliable, much more cost-effective for internet, much faster by far, and they turned off their satellite connection as that wasn't necessary. But I'm going to give you the opposite side of that, in the sense that we may have a working internet, but every now and again it breaks, and it breaks again at the physical layer, which may or may not have a real-world consequence. if you've ever looked at streets and seen lots and lots of spray-painted lines with either sort of cryptic letters on it or otherwise, that's underground services marking a road or some area and saying below here by a certain amount there are certain things. I picked an easy picture here. This one uses the word gas, which is, by the way, normally in yellow, electricity, which is normally in red, and then communications that is white or equivalent. And so this is a road. If you're going to dig it up, be careful, because you are going to hit a gas main, you're potentially going to hit an electricity line, and you're going to hit a fiber optic cable, which will have something to do with the internet or a mobile service or equivalent. And, well, on the right here, you see exactly what happens. This picture shows a classic problem of digging, eating up a whole bunch of cables, causing a right royal mess, and somebody has to get out there and fix that, which in the fiber optic world actually means patching in new cables and making the light flow again. An interesting side point, a lot of players have worked out how to bury fiber optic cable very reliably, and that is that they bury it below a gas line. Because out of all the things that people dig up, people seem to want to avoid gas lines. But this is some of the negative side, and hopefully with multiple paths, the BGP protocol keeps things going. But we're all fairly aware that we do hear about outages on the internet caused by some physical device. So far, I've really only talked about sort of the physical side of this and the network side. In the networking world, we actually go up and up and up the stack. Simply put, the pictures I just showed you were from the data layer, from the physical layer. The BGP, the routing I talked about, is from the internet layer. But above that is the transport layer, the ability to actually use that network and generate a communication that's useful for an end user. And then finally, above all of this is the application, whatever you have on your mobile phone as a website or an app, whether you have a bank that talks to another bank over the internet, all of that is at the application layer. And I'm going to stop really at the internet layer because that's where I deal with this area. So 2 things to tell you about, and then I will hand this over. One is that the internet, well, the internet's a global phenomenon. It exists as much here in Silicon Valley as it does in just about every other country in the world. But the world's quite large, and it takes a lot of time, basically because of the speed of light, to move a bit around the globe and get it from one place to another. The speed of light we can't do anything about. We really can't do anything about that. But there are some techniques that make the beginning of a communication much more efficient than worrying about these type of connections. But from my point of view, from the infrastructure point of view, we have to deal with reliability. And reliability does have a function, a loose function, on the number of hops, the number of devices that you go through. Because the more devices you go through when, let's say, going from a data center for a cloud operator on the west coast of America to an end user in Mumbai, India, you end up with an awful lot of moving parts, an awful lot of vendors even. And so reliability has this inherent decrease, and you have to go work on that. But we do have redundant paths, and that actually exists in just about everywhere in the world. And we do have variable providers. In other words, we can go out and buy commercial contracts, and Cloudflare explicitly does this, with multiple providers, so that we not only get diversity of physical path, but sometimes we get diversity on something that fat fingers or is a mistake. I said I'd talk about tools. This is the last part for me. I'm going to give you sort of 3 pointers and homework in a way, but I truly believe each of these is fairly simple to use in a different way. The first tool I'm going to point you to is a tool from a company called Hurricane Electric. It's the bgp.he.net website. The URL's at the bottom, and I already heard that we're going to distribute the slides, so it'll be there. This site is very simply, an ability to bring up those diagrams to look at a network. Have a look at your own network. Have a look at your hosting provider's network. Have a look at your competitor's network. Do whatever. It should have all 60,000 networks of the global internet in there. It contains a lot of useful statistics to show growth, but it can be very useful for putting an IP address in, working out where it is, and seeing how it operates on the routing tables. The second one, the middle one, is the RIPE Atlas tools. Now, the RIPE Atlas tools may take a little bit of effort to learn how to use, but there's a lot of static information available there already. A RIPE Atlas is based upon a small probe, a computer that's no bigger than hopefully about an inch by a little bit more. And you pop that on a network, whether at home or in a company, and it just sits in the background doing tests, just small, light tests, all collected by RIPE in Amsterdam and then correlated in some useful manner. And you can run your own tests. You can test against your own website. You can test against your hosting provider. You can test against whatever you want to your name service. You can build tests. And again, follow-up reading will be from that URL. And the final part that I want to talk about is another form of data. This is, in fact, a good example of where data for the world of BGP, the world of the internet infrastructure, is kept. One of a few. So again, I go back to RIPE, based in Amsterdam, the stat.ripe.net site. You start just by typing in an IP address. It'll give you some useful information. If you found something that had been unreliable yesterday but looks okay today, again, you can start using IP addresses or network names to drill down. And one of the things that even if you're new to the world of sort of internet infrastructure and BGP, there's a very simple rule that makes sense throughout the world. If you look at a graph and it's fairly stable, that's a good thing. If you look at a graph and it has an awful lot of blips up and down and left and right, or worse still, some red areas in it with something bad going on, well, then you know you have something more to drill down on. And all three of those sites come in some way with either presentations available online or blogs that would help you. So I'm hoping that this has given you sort of an understanding from the network strategy point of view of what a bad day is like. But I will stress what I started before I hand this back right from the beginning. Most of the time, if not 99-point-something of the time, things are good. And that's the way it's meant to be. But today I took the advantage of talking about some of the issues and expanding upon them. Tim, back to you.
Yeah, great, thanks. I'm going to play a little devil's advocate and then sort of sum up what you said. So you talk about some of the causes. So one of the ones at the top of latency was just distance, speed of light. And so and it sounds like typically that's just insurmountable. If you have it takes you a long time to get somewhere, it's going to take you a long time to get there. There's some physical boundaries to that. The second one was you talked about there's BGP, and then you also talked, so that's your routing, and you have multipath, but you also have some scenarios where it's down. Why is there a problem? It sounds like that's good. We have multiple paths, then we just pick the fastest route because we have this multiple path, or do we ever have a situation where I'm trying to send you one way and it's actually way slower than it should be? What seems like it's actually designed to get us there faster. Can you elaborate on that?
Absolutely. To do with your first part, yes, the speed of light is the speed of light. Interestingly enough, when you put a signal into a fiber optic cable, which is what 99.99% of the internet is built out over, it actually slows down. It slows down by about a third of its speed. That's to do with the refractive light. You learned this at physics in high school. No one actually remembers it, so we'll leave that for a Google search later. However, above that, and I think Nick will deal with this, you can get protocols that don't have to go backwards and forwards over these long distances in order to solve, in order to shorten that.
So slow down that part. Sometimes when someone wants to get there, it's not just I go from point A to point B. You elaborate a little. You talked a little about protocols. Sometimes the way you establish that at that data and the internet level is you have to go, say it's okay, hi. Yes, I see you. I come back. Oh, it's you. And so there's a back and forth.
Yeah.
You traverse multiple times to go from point A to point B. Is
Right.
that correct?
That's correct. In the basic TCP world, it can take 3 packets to flow from the beginning to the end in order to confirm a conversation. In the TLS world, in the secure world, it used to take upwards of 13 packets.
Mm-hmm.
So now imagine that it is 200 plus milliseconds between the west coast of America and Mumbai.
Mm-hmm.
You could now be in the multiple seconds to get a secure connection going before any web page or communication has occurred.
Right.
We'll deal with that.
Okay.
So that tees up sort of what Nick wants to talk about. However, your other question about the redundancy was a good one. Yeah. Routing protocols come from actually sort of deep mathematical and scientific processes. BGP deals with the path, the ability to know that there's a path between A and B. It does not take into account the capacity issues.
Cool.
So sometimes you know that you can get from here to there, but you don't know the pipe is full. Right. So we have to throw a lot more expertise into the network, and that's a whole other seminar.
Yeah.
And we'll leave that one for today. Under most circumstances, using over-provisioning and using high amounts of redundancy, we really don't touch those issues. And that's by design, quite frankly.
Okay. All right. So to summarize, it's kind of like I'm getting from point A to point B, and I'm using Google Maps. If I have to go from here to New York and I'm walking, there's that distance. There's that just inherent distance. However, if by the nature of how I get to New York, I have to go to New York first to tell me where in New York I have to go, walk all back home to San Francisco and say, okay, now you got your luggage, and then I go back to the network, that's taking more paths. That takes even longer. And then the third one which is, hey, I know how to get to New York, but each along the way, maybe every state, I then figure out, well, how do I get there? And at each point that I stop at the border, I have 3 paths I can go. It just tells me what those paths are, but doesn't tell me like in Google Maps, hey, don't take this path because it's going to take you 36 hours longer than the other path.
Yes, and that's really the goal of the network engineers to engineer this properly. And in fact, in the networking world, you start doing things much more efficiently so you don't run a path that's thin and a path that's thick next to each other.
Yep.
Because you want redundancy.
Yep. Cool. All right. So let's tee it up and chat with Nick. So Nick is on the engineering team, and so this is really a great opportunity to hear how these problems get solved, how he thinks about them at the engineering level. So Martin talked about the set of issues that we have, and we're going to turn it over now to Nick.
Yeah, great.
Hey,
Thanks,
Nick.
Tim. Hey, how are you?
Good. So we've got problems sometimes, as we talked about. How can we address these? How can we make the internet more reliable?
Yeah, absolutely. So Martin, he really talked about how he operates at these sort of lower layers of thinking about the internet, the physical links and routing layers. And I work in the engineering team at Cloudflare, where we kind of think about the top half of that stack. We're thinking about how do we address some of these problems on top of that infrastructure to provide higher reliability, more performant web applications, APIs, et cetera, for our customers. And so, one of the things that we're thinking about, how do we solve some of these problems around reliability and performance in the internet? There's this, maybe we could take a really broad look at, well, can we just change the model of the internet? Martin kind of alluded to early on the way that the internet was conceived of was this, group of academics, small group, and it was at a time where the sort of rare resource was computation power. So there were these, high performance servers in very specific locations that could do lots of scientific computation. And so one of the problems was, how do we make these rare resources, expensive resources, available to broader sets of people? And so one way to do that is to connect these specific servers to a network that other people could connect to. As computation became cheaper and started being widespread in personal computers and laptops and cell phones, now the compute is not the rare resource, and really what we've evolved to use the internet for is content. Give me that image, that video, run this query on this data set. And so this model of thinking about the internet as I'm addressing a particular server to retrieve a resource, we flip that on its head and instead think about, well, I just want a resource. I want that image. I want that video. And I just want to ask the network for that content without actually having to care about where it exists. Kind of an equivalent analogy here would be, before everyone had a cell phone in their pocket. If I wanted to, Tim, if I wanted to call you, I had to know, are you at home? Are you at the office? Are you at your favorite restaurant down the street? I'd have to know that specific location, call it, and then ask for Tim. But now everyone has a cell phone in their pocket, and instead I can just pull my phone out, and I don't even have to know your number myself. I just press the button that says call Tim, and wherever you are in the world, I reach you. And so there's been some academic study, and there are some companies now starting to think about how could we build this new model of the internet where we think about addressing content rather than addressing servers. One of the big challenges here is that, of course, this changes a lot of those lower layers, the routing layer of the internet, and how we think about moving data, and so that would require a lot of reinvestment in new infrastructure and new protocols. So it's going to take a while before any of these sort of strategies really take hold. So if we can't really change the conceptual model of the internet, what's something else we could think about? Well, so what about some of these lower level, these core internet protocols? So if we build a better BGP, what would that look like, right? And so some of this is thinking about, as Martin just referred to, is thinking about capacity and thinking about sort of global performance and these sort of metrics that applications that run on the internet today really care about. And one of the challenges there is that we have these many networks that are all interconnected and all have to agree on not just the protocol, but what are the metrics that we care about, and how do we think about the optimal way to move data through all of our disparate networks. And there are different incentives and different ways these different providers think about the benefits or trade-offs of different routes through the internet. And so kind of thinking about solving this problem, it's not clear, there's no direct correlation of here are the metrics that we could use to augment BGP to provide higher reliability or more like global performance guarantees. And we think about maybe even a step higher, the transport layer. So TCP is a very common transport protocol that a lot of these applications on the internet use just to move data reliably, to make sure that if I want to get an image from that web server, that I get the full image and I get all of the content back reliably. And so TCP and UDP, they have their own problems. TCP in particular has a lot of logic built into it around trying to detect when congestion is happening and responding to packet loss. And these protocols are really hard to change because not only are they so widely used in applications, but also built into a lot of, again, the growing infrastructure of the internet. These devices like firewalls, load balancers, network optimizers, they all are kind of built to monitor and understand these specific transport protocols of TCP and UDP. So we sort of have this problem of, there are things that we could do at these lower layers to improve the internet, to get higher performance, higher reliability, but we have a lot of barrier to make progress there. And so the way we think about this at Cloudflare is, from the engineering side, is we want to think about an evolution of the network protocols, not necessarily a revolution. We're not trying to rip something out and completely replace it. But we want to think about how can we find easy places to add something on top of what currently exists to solve some of the problems at the lower levels. And so there are sort of the higher layers of the network stack, the application layer. It's a lot easier to kind of think about changing what's happening there because it's not going to require sort of hardware or infrastructure changes. And so a good example of this is TLS 1.3. So TLS is a secure encryption protocol that is used very broadly over the internet, most specifically in HTTPS, but also in any other protocol where we're trying to send data securely. And this 1.3 variant of the protocol, not only does it add some features that make it more secure, it also is an evolution of the protocol that is thinking a lot, that shows the thought of trying to make the protocol faster. And so it requires fewer round trips. Martin said there were 13 packets or something at some point to get a secure connection. For TLS 1.3, it might be a single round trip for the first time you establish a connection between endpoints, but then on subsequent connections, you could reuse certain credentials that you've negotiated in the past to start sending encrypted data without requiring any additional round trips. So this is really acknowledging this problem of sending data broadly across the globe and trying to reduce the number of times you have to suffer that latency of long distance. Another good example is TCP and HTTP as the transport and application protocols, replacing those with UDP and QUIC. So QUIC is an application protocol developed by Google that attempts to solve a lot of the problems that make TCP slow, and in particular in an ecosystem where you have a lot of web traffic. You have short-lived connections, many resources, a lot of dependency where I need to load 3 or 4 different resources at the start of loading a web page, and there may be another 20 that follow behind that. And so it implements a lot of features to address some of the problems in TCP and HTTP, like connection establishment, again, session multiplexing. So these things that allow us to take advantage of only establishing a connection between endpoints once without having to spend many round trips every time we want to request a web resource. It also attempts to sort of reimagine some of the congestion control mechanisms in TCP that can cause it to sort of behave poorly in cases where there's even just a small amount of packet loss. And it also implements this very interesting forward error correction mechanism, which basically encodes information in every packet about other packets that are coming next. So that if one gets dropped, then the peer on the other side can actually reconstruct that dropped packet from information packed into the other packets. And so, it's thinking about these ways to reduce the impact of even a single dropped packet on retrieving a full resource. There's other flexibility and other types of enhancements in that protocol, but this is a way that we could think about, taking the transport and application protocols and swapping them out for something better that solves a lot of those problems of latency and reliability. So these are just a few examples in kind of a broad class of evolutions that are being made. And the real challenge here is distribution. So in order for me to use QUIC, I have to have a web browser that supports QUIC and also be communicating with a web server that supports it. And if you want to adopt this for all of your customers as a web property owner, you need to think about how do you get that adoption and get all of your users to adopt these new protocols. And that's generally a pretty challenging problem. So as an application developer at Cloudflare, one of the things that's really interesting is we have this very large global network. So we have points of presence, data centers around the globe, and we're adding more every week. And we're really getting them very close to every internet user and every server on the internet. So we have proximity to every endpoint on the internet. Also in every POP, we have multiple transit or peering relationships with all these different networks. So in order to send data out of a particular POP, we don't have just a single sort of route or a single path we could take. We actually have options that we could select between. And we also see a large percentage of the internet. Cloudflare proxies about 10% of all web requests. So this gives us a lot of visibility into sort of real-time what's happening with performance and load and capacity on the internet. And so this gives us a really good platform to monitor performance, reliability. We can get sort of real-time feedback as this data traverses our network about what's actually happening on the internet right now. With this footprint, we can also think about testing different paths that BGP wouldn't necessarily tell us to do. We can sort of influence and say, hey, what if I went left instead of right here? Does that actually get me to the destination faster? These sort of mechanisms allow us to really look at what are the performance metrics, like measured performance metrics that actually matter to a web application. So things like time to first byte, the time to serve a full HTTP response. And so some of the interesting things we can do with this global footprint, in this diagram here, we have a web user in Eastern Europe, and he's trying to communicate with a web server that's on the west coast of the US. And that black line on the bottom shows maybe a path that BGP would have taken, which is about 200 milliseconds away. With Cloudflare, that web user will be directed to a POP that's close to them. That's the blue pin on the far right up there on the orange path. And then from there, we can look at what are the ways that we can actually pin that, that path through our network to kind of influence the route that's taken. So Tim, you used an analogy of Google Maps going from San Francisco to New York. So this would be like equivalent to saying, if I am taking if I ask Google Maps for that path, it'll tell me all the roads to take. But I might know, that interstate tends to be congested around the time of day that I'm going to be on it. And so instead, I'm going to tell Google Maps, hey, why don't you send me through Kansas instead of Nebraska? Because I know that that's going to sort of inform a better path through sort of the entire link I'm trying to traverse. And so we have these different options for finding all these different paths through the internet and pinning them through our different locations, which might allow us to find, for example, a path that is substantially faster just from a sort of one-way latency perspective. So in this case, 150 millisecond path. Another thing that this allows us to do is, on that same 150 millisecond path, we can pin that through POPs that are both close to the internet user and close to the web server. And this gives us a distribution channel for some of those evolutionary steps in the application layer and the transport layer. So while it would be very difficult for Cloudflare to get every internet user and every internet server to adopt the QUIC protocol, if we can get the traffic from that internet user and the server to data centers, to POPs that are closest to them, we have this long link of the internet through which we control both sides of the connection, and we can deploy our own updates and use things like UDP and QUIC or other enhancements to the internet stack. And so, through these mechanisms of sort of using the global network, our visibility, our physical presence, being able to kind of inform the routes that happen at the lower layer, as well as making these improvements to what's happening at the higher layer transparently without requiring our customers or end users to change anything on their end. We have a lot of power to change and improve the performance and reliability on the internet. Cool. And with that, I'm going to wrap up and pass back to Tim.
Yeah, that's great. So, so there's some questions that have come up here, and I want to tie it to this picture. But to tie together for this, so Martin painted a picture of, hey, what happens when there's congestion? How do I route? How do I limit this back and forth? And then how do I address sort of issues of distance? So this picture and sort of the solutions that Nick has been engineering is actually a good way to address those, because as you can see, he reduces the amount of back and forth by allowing multiplexing. He's having some routing suggestions where he says he improves upon the locally optimized paths from BGP because he has visibility across all the traffic, so he actually gets you to the place that's not congested when somebody cuts a cable like Martin described. And so somebody asked, hey, so does that mean, how do we get people to do all this without changing the internet? And Nick sort of described that as, That's hard to do, but look at what happens when you have an existing global network. Cloudflare then does the things that make things smarter, so that if you're using the Cloudflare network and other people are then accessing that same thing, we actually provide, call it an overlay on the internet that addresses some of these problems. So, for example, somebody asked if there's a bottleneck identified, can traffic be prioritized? And that's exactly what Nick described, is he has visibility across the traffic along paths. He's able to then, he's designed a system which helps to actually optimize a path that still uses perhaps either the BTP routing or, in this case, our own inter-pop pathway, which may be faster. So to answer that question, Cloudflare, by having so much traffic and by being able to determine the routing as well as the transport layers, is able to solve that problem. So hopefully that answers that question. So that was, you don't have to rewrite the internet. Cloudflare already has a chunk of that path and is able to actually solve for that. I'm going to throw a question over here to sort of share some of the things. I'm going to pick off some of the quick questions and then throw it back to Nick and Martin. So how would you be able to leverage that? Somebody asked, well, what do I actually have to configure in terms of the switches or the firewalls to work with Cloudflare? And so in terms of us, when you have the DNS, that sends the traffic to us, and then once you're on, the traffic is within our network, this diagram that you see from Nick pretty much kicks in. I don't know if there's any more detail I can throw to Martin or Nick if they want to address any more issues around their own switches or firewalls, but I think once you direct traffic through DNS, it goes to our edge instead of you first.
Yeah, that's right.
Yeah, I'll hit one important point about that. While we deal with the delivery of the bits towards the eyeballs, towards the end users, there's still the task of bringing the content in from the origin.
Sure, right.
So independent of which part of the process you look at, all of this plumbing is still part and parcel of the equation. There are some things that we do to assist the origin. So let's say that's on a generic cloud provider or a hosting provider, or maybe self-hosted, as that still happens. In all cases, as long as there is good, clean communication for the website that we are replicating, that sort of first hop part that's in the diagram on the screen, then all is well. But we do actually, through our API and through our website, we do provide a set of IP addresses that you can set up on a firewall if you want only the web content to be accessed by Cloudflare. Yeah. We can go one stage further because we do origin certificates now, and so you could actually lock down the TLS communication. This is much higher level stuff. The plumbing is well below that. But ultimately, there are two things that are happening here. One, getting the bits in efficiently, and two, protecting the bits to make sure that the right people are talking to them. So there are some things that we provide. I think we've probably written numerous blogs on the subject, but that would be an area. So under 90% of, if not 99% of situations, there's nothing that needs to be done on the router, on the switches, even on the web services for the origin. However, we do provide some value add in there for optimizing and protecting as necessary.
Yeah, cool. Nick, did you want to add to that?
No, I think Martin covered that pretty well. I think just one other thing to note as a footnote here is that in September we also announced a product that we're working on called Cloudflare Wharf, which will actually take your origin completely offline. You don't even need a publicly addressable IP address to connect to it, and so that's just even another layer of security through which we can guarantee that protection to your origin and only traffic from Cloudflare's network will be allowed to reach it.
Yeah, cool. If there are any other questions, please feel free to jump on in. We're going to be wrapping up shortly. So here's an interesting question which I've been interested in. I'm going to throw it to you guys here. Someone asked about Canada. Slow, and this is not just Canada, there's other parts of the region where the internet's typically either slow but really also expensive. you want to talk a little bit about that cost and speed trade-off and how some providers and regions tend to have those issues? And then Nick can jump in a little bit about how some of the things that we address those, because we see that, because we see traffic across
right.
the globe.
So, not wanting to pick on Canada.
Right, yeah.
But, as it was brought up, there's actually a couple of great examples, Canada, Australia. And I'll pick these two because they're sort of easy places to visualize. A vast majority of the population lives near a particular feature. In Australia, they live close to the ocean, predominantly on the east, where Brisbane, Sydney, Melbourne is, and to the south where Adelaide is. And very few live in the middle of the country. Or even if you drive 6-7 hours inland from anywhere, well, things start getting fairly sparse. In Canada, majority of the populace lives near the border, their southern border, and as you go north, and it is a vast north in Canada, you end up with far fewer people. That density has a financial impact on how you build infrastructure. Oh, plus the speed of light, going back to the previous conversation, that doesn't go away. And so in reality, it is natural for the phone companies, for the mobile companies to focus where they have customers, and things just get a little bit more sparse. How do we deal with it inside Cloudflare? Let's take Canada, for example. We have content delivery nodes built into the major cities such as Toronto, Montreal, into Vancouver. But at the present moment in time, we haven't headed up to Calgary or to Winnipeg, or definitely if we go further north to places that are much fewer people. There is, to be honest, an economics associated with that. There's no doubt about that. In Australia, we started out with one node in Sydney, and then we added Melbourne, we've added Brisbane, we've added Perth since then. And we'll probably add one or two more into Australia just due to its size. And we service New Zealand, for example, with its own site. And you can replicate this conversation around the world as a function of where people are, the economics of putting something somewhere, and the ability to build the backbone, still be able to get the bits in there. So you could definitely put a dot on the map and say, we need to move bits to the middle of the Sahara. But it turns out moving bits to the middle of the Sahara is actually quite complicated, and therefore even we would have a hard time delivering one of our nodes in there. So you have distance, and you have population density, and you have natural economics of how phone and mobile companies work, where as you go further and further afield, your connectivity becomes either slower or simply you have no options. That said, you know, there are full links to the base camp in Everest now, all the way back to Kathmandu, so you can sit in your tent before a climb and have full access to the internet. It's getting harder to find places on the globe where there isn't some form of good connectivity. Yeah. But good is a very different definition from where we are sitting today to some of those places.
Sort of related to that, someone was asking how does the internet exchanges fit into reliability? And I think that's an interesting thing for us in terms of how we leverage the internet exchanges in terms of related to the cost as well as speed. I was wondering if you could jump in on that. So his question was how does it fit into reliability? I think the underlying question that leads to is how does Cloudflare use the internet exchanges, and what's the impact in terms of, you know, cost and bandwidth?
Right. Cloudflare is by far one of the largest users of internet exchange points anywhere in the world. We eclipse anybody else that's doing content.
Maybe explain what they are.
Yeah, sorry. So imagine a place where lots of networks can meet equally and distribute traffic. An internet exchange point is where three or more networks join in a common infrastructure, normally built out of high bandwidth Ethernet switches these days, in a common location. So let's say a data center where lots of other telcos exist. And the express purpose of an internet exchange is to allow one connection into the Internet Exchange to communicate with multiple Internet networks at the same time. It's actually quite an economically viable thing to do. If you imagine 3 telcos sitting inside the same building, you could run 3 wires in a triangle and they'd be connected. If you had 4 networks in a room together, you go, oh, maybe I need to run 6 wires because you have to connect everyone to everyone else. Right. Pretty soon that becomes just untenable. So the solution is that you have one common provider, an independent provider normally. They run an Internet Exchange. And as I said, we connect to about 160 plus of these and growing around the world. And we will connect sometimes to places that have 4 or 5 players, but they're important. Mm-hmm. So let's say a point like the island of Curacao in the Caribbean. There's only a few players there, but they're very important. Mm-hmm. Or to a place like London or New York or Hong Kong or South Africa in Johannesburg, where we connect to hundreds and hundreds of different networks. So the economy is phenomenal at that point. But more importantly, the moment that lots of providers show up in a single point, you get this effect where more providers show up, a network effect. It makes it even better for other networks. So the optimization of the Internet in a place like Hong Kong or Sao Paulo, Brazil, or London, or in Seattle, or in Toronto, or in Miami, has grown rapidly because of Internet exchanges that exist there. And we use them. We use them to distribute traffic. We use them to collect traffic. They normally have a great function where the cost effectiveness, which is important, because we want to be able to provide a very cost-effective service, it makes it very cost-effective for us to move bits. Think of the analogy in the road system of a roundabout. Yeah. No, that's a very British thing, or at least New England. Yeah. Many roads in, a big circle, many roads out, yeah. And you can go in on one pipe and come out on whichever one you desire. Yep.
Viewpoint circle. That's great. Cool. Okay, we're going to wrap up here. For those of you, even if you don't have a question, I'd be curious, what was something that you guys learned that you didn't know that was helpful to you as an IT professional? Something that you can either chat with other people or made you rethink about how to solve your application? And I don't know, maybe we'll come with some kind of prize. I have to think about that. But chat in there and tell me what you guys have learned. Thanks to Nick, systems engineer, who's been working hard at solving these kinds of pretty hard problems, and Martin for giving us really, this is kind of information that's actually hard to find, how the internet actually works. I think this is really a great treat for us to understand those pieces. If you want additional information, here is some stuff on our blog, which Martin had mentioned, that talks about the different features and problems, as well as some of the products. We really haven't spent much time talking about products on this. We really just want to talk about problems and solutions. But we're getting ready to wrap up. Thanks all for joining. Still share what you thought was something really interesting in the Q&A, and if I see something really interesting, maybe we'll figure out a prize. But I'd love to hear what you guys thought. This was something that's a rare opportunity to understand how the internet works, why it's slow, and how to fix it. Thanks, everyone, and we're going to wrap.
All right, fantastic, guys. Thank you so much for that presentation. Hopefully everybody was able to learn a bit more. So I do want to let everybody know that if you had to step out or you missed any part of this presentation, you'll be getting an email from us in just a couple of days with a link to check out the recording on demand. Also, if we weren't able to get your question live, somebody will be able to follow up with you. I want to say special thanks to Martin and to Tim and to all of our presenters for this great presentation today, and hopefully everybody was able to learn more. Special thanks to each and every one of you for tuning in today. We hope to see you back soon for another SpiceWorks Partner webinar. Till then, stay safe and keep it spicy.